Okay, so we're going to talk about set operations. Okay, now what's an operation? An operation lets me take two things like R1 and R2, and I'll call the operation here circle plus. Okay, and the result of this is a new relation. Okay, so an example of that is arithmetic operations, right? And arithmetic operations take two numbers, A and B, right? And these things are numbers. That's the arithmetic part, right? And we have some kind of an operation, again call it circle plus, and the result of that operation is a number. Okay, so you see it's the same sort of thing. We just have two relations. We're going to do something to them, and the result of that will combine them in some way, right? And the result of that is going to be a new relation, right? So that's what we want to do, right? So here's the very first example of a relation, right? So of an operation. And what we're going to do is we're just going to take all sorts of sets operations. Okay. Now, set operations, this would be things like union, intersection, set difference. Okay. And what we have is that since relations are sets, then of course I can think of them as sets. And actually, it's like the union of two relations or the intersection of two relations, right? This will work as long as both R1 and R2 are relations over the same sets, right? So for example, let's say that I have a relation between students or majors and another relation between students and cars, right? I can't just take the union of those because, well, that's adding apples and oranges. So this notation is one that we've actually been using all along, right? You may remember when we said S2 is equal to S1, scratch it up. R2, relations. R2 is equal to R1, union, the set of all, right? Remember that when we were doing closures? There we have a set operation, okay? So we've kind of been doing that since the beginning without really mentioning it, okay? Now here's an important operation, and that is the inverse of R, right? And I'll show you that it actually has a symbol, is R to the -1, okay? And what we do is, if you think of them as tuples, right? Then what we're doing is just simply flipping them, okay? So let's say that I have a relation between some set S and T, and it goes like this: A, 3, B, 5, C, 1, okay? Then the inverse is going to be a relation from T to S, right? Notice that the columns are flipped. And we'll have 3 goes to A, 5 goes to B, 1 goes to C, right? And so that's it, right? We just kind of flip two things. And we'll talk later when we talk about functions. This is actually very, very similar to the notion of a inverse function, okay? Right? Simple example of that, less than, then when you flip it, you get greater than, right? So 1 less than 2, 2 greater than 1. That's the inverse relation. Okay. Now, this is a slightly fancier relation, okay, or I should say operation between relations. And what we're going to do is called composition, okay. And if you remember composition of functions, right? We had F circle G, right? There's the composition symbol, and that is this is a function. So notice what's happening. I'm taking two functions, combining them to create a new function. This is a function operator, so function composition. And it was defined by f of g of x is equal to f of g of x, right? Okay. So this is in fact very, very similar. And what we're going to have is we're going to have these multiple tables, R1, right, and R2. Okay. And we're going to build, let's say that this goes from S to T, okay, and this one goes from T to U, right? So what we'll build is R2 circle R1, okay, that takes us from S to U, right? Let's say that we go from A to 2 and B to 3, and these are not meant to be unique, so let's say B to 5. Now we'll go here and we'll have 1 to Z, and 2 to Y, and 3 to W. Okay, so the way that we'll do the composition is as follows. We'll start with we'll start with an element of S. We'll go and we'll get the 2, and then we'll line that up with something in R2. So we'll go from A directly to Y. Okay. Similarly, from B to 3, right? So I'll just take this down here and get the W. B, I can get to W. B to 5, that doesn't get me anywhere, right? If there were other elements here, like for example, if we also had, let's just add 1 X, right? Then I would also go from A, I'm sorry, take that back, I'll make that a 2X. So from A to 2 and to X, and we would have that, okay? So you see, that's how we combine these, all right? So this is composition. This is a composition of two relations to give me a new relation. Okay, if only we had this before, because we were doing these crazy things like R1 is equal to, actually let's start with R2. R2 is equal to R1 union, right? The set of all A, B such that, right, there exists a C, A comma C belongs to R1 and C comma B belongs to R, okay? But actually I could have just simply said R2 is equal to R1 union R1 composition R, okay? That was it, right? So this is actually the same operation, much more compact. If only we had this before, we would have saved ourselves some effort, right? But realize now that it's actually pretty easy to work with compositions. Okay. One more operation that I want to show you, and this is called, well, a couple more that I want to show you. But this one here is called projection, okay? And projection works, it really only works when we have like more than 2 attributes, okay? So let's say that I have S, T, U, and V, okay? Those are the sets that I'm combining, and this is an A1, Z10, right? And we'll have B2, Y15, and so on, right? Just a whole bunch of elements, right? So now what I might want to look at is project on SV, right? And the result of that is just this, right? Effectively what we're going to do is we're going to hide this, right? Because we're projecting on S and V, right? And so we're left with just those 2 columns. A10, B15. That's it, right? That's a projection. Okay. So formally we say it's the set of all xz such that xyz belongs to R. I notice that I dropped off the y. I don't actually keep it, right? Projection, that's an awfully weird term. Actually, it makes sense because what we're really doing is projecting kind of on the plane, right? So let's look at this example, or rather this picture. This is a 2-dimensional plane, and I can think of a vector being here that goes out like this in 3 space. So I can now take the projection of that onto 2 dimensions. And there it is, okay? So I only have 2 dimensions, so I only need 2 coordinates to do that. That's where the work comes from. All right. One more that I want to show is called selection. Okay, selection is one word for it. The other one is filter, right? And what we're doing when we do this is we're simply adding a condition. So, for example, let's say that I have a relation R that looks like this, and I'm going to have a relation between people and major, okay? Right? Yeah, I may have Mary, who's a math major, and John, who's a computer science major, and so on, right? And what I'll do is I'll want to project on majors in CS. So we only want the majors that are actually in the engineering college. So we have a table or a relation. This is a projection, okay, over the same attributes, okay? But now we're, let's see, is this in CS? No, that's not in CS. Yes, that's in CS. So I would have John Cosi, right? And whoever else. But I would not have Mary, because Mary is majoring in mathematics, which is not in the College of Engineering. Okay, so that's projection. I'm sorry, this is selection. That's another kind of operation that we can do on relations. Okay, so quick spoiler alert. I also happen to teach the database course, and the database course we primarily, as in 13 out of 14 weeks, we talk about something called relational databases. Okay. What's the relational databases? Well, they organize their data into something called relations, right? Also sometimes called tables, and as you know, I use those words interchangeably a lot, right? And what these look like actually is, for example, just what we did, where we have students and majors, right? That would be a relation or a table. And we have John majoring in COSI, and Mary majoring in math, and so on. Okay, this is a relation in a database, right? It's also a relation in mathematics. It's not a surprise. That's where the word comes from. Okay, and here's the thing: when we study relational databases, then we got to talk about some operations on those. Okay, so we'll talk about relational algebra. And relational algebra, what does that mean? Well, this word actually just means operations on, right? So for example, when you took algebra in high school, that was the study of the operations that work on numbers, right? So you studied, you did, for example, x squared minus y squared is equal to x plus y times x minus y. That's because that's the way those operators work. That is always true when you use plus and minus and times in those ways, okay? So the kind of operations that we do in relational algebra, in fact, are set operations, okay? Also projections and selections, okay? Those are kind of important. And then the most important one is something called joins, right? And it's actually written like this: R1 join R2. That's supposed to be a bow tie symbol, okay? And joins are actually almost exactly like compositions. In fact, they're exactly like compositions. Okay, so shoot, the operators that we talk about relations are in fact the same operators that we'll use in relational algebra when we talk about relational databases, which is actually just the theory of relations that persist on disk.